quite in itself. Alright. So guys, today in this lab, and what's what we're trying to do? This lab is, we're trying to find the acceleration of a car, right? But there are a number of ways of doing it depending on the equation you choose. So if you chose an equation that had, that was, you all know the delta x equation, right? This is the first one. If we chose this one and I'm starting from rest, then my VI is going to be 0. Even if I choose this one, VI is also going to be 0.
No, it's going to be 0 because you always start from.
We always start from rest. So all of these, when I did this the first time and I was showing you, I just got rid of these and I said, okay, delta x is going to just be equal to just this. Vf is just going to be equal to this. Vf squared is going to be equal to that. Now, because I designed this experiment to use a meter rule and a timer, like on your phone or something, I chose this equation over these because choosing this equation, I can measure delta x using a meter stick. I can measure time with a timer or stopwatch. That's easy. But these are the two. I would need a motion sensor for velocity, and I need a motion sensor for velocity here.
You don't have the variables for it. You don't have the.
And we actually do have it, but I was thinking to introduce you. This is our first lab, so I wanted to introduce you to the lab, and go with the most rudimentary things you can even do at home. You can use these at home. You have these at home, right? So we chose this one. That's why I boxed it out, and I wanted you all to say, okay, you have to now choose your dependent and independent variables for each of these. So we're going to do it just for this one. So the dependent variable, which is the y-axis variable, was going to be
my delta. Equation of x because you have the negative 3, so you can measure that.
Right, so the independent variable, the one that's just running, is going to be your time. Right? Now, what we're going to get, I want you to tell me this. If I just have delta x is equal to half at squared, what shape is that going to be?
I feel like it would be just a parabola.
Like a parabola.
Because you already have the square and everything's going to be times squared.
That's the key. It's going to be dependent on t squared, right? It's going to have t squared in it. So it's going to be a quadratic relationship.
Yes.
And it's going to look like a parabola. So when I draw this is what it's going to look like if I go just to t. Delta x against t.
Yeah.
But it's going to be harder for me to find a if I have to depend on, okay, now it has a t squared in it and it's a little off. What if I use this whole thing, I square the whole t?
It'll be a line graph and you'll have a rest.
I'll get a line graph, exactly. Why? Because it will look delta x equals to half a t squared, where t squared is just like an x value.
It's just a value, yeah.
It's going to look like this. It's going to look like my straight line graph. So my y is going to be my delta x. My m is going to be like my half a. And my x is going to be my t squared.
Yeah.
Right? And that's going to go to 0. So that's why we're going to try now, that's why we're going to collect this data now, to say, okay, for each of the distances along the track, we're going to have a different time. And then with those times, we're going to square them, and then we're going to plot this against t squared, this against t squared, this against t squared. And
that's where the line graph will
be. Correct, that's where we get the line graph. Does that make sense? All right, so let's see how you would do it. So let's start at 90.
Which would be 0.9, right? Yeah.
So this is 100, this is going to be 10. So this is our 90 measurement. All right? So you're going to catch it on that side.
All right.
And let's get our first measurement.
1, 2, 3. Okay, we got 1.16.
All right. So let's do the next one.
All right.
Let's get AD and see if it matches up with what we got. Yeah?
All right, yeah, so 1, 2, 3. That's quite weird because I go 1.3.
Okay, so we got 1.3. So let's do that for 1. I'm going to write it in the corner here. And let's just see how it progresses.
All right.
Right? We want to just observe it. Let's go.
1, 2, 3. Okay, I go 1.03. Sorry, I go 1.03.
03? So it is going down. So that's good. Alright? It's supposed to go down, right? So it's less and less time.
Yeah.
Right? Makes sense.
Because it's just changing the displacement. It's gonna be shorter and shorter.
Shorter displacement, same force is acting on this, right?
So the objective is to get like a smaller number each time, right?
Yeah, well you're expecting, that's your expectation, right? So let's go. Let's go for
1, 2, 3. Okay. I got the same number though.
That's okay. Because now don't forget there's errors between you and me.
Yeah, exactly.
Maybe I'm not syncing up in time with you or
Should we just try again?
you try it, let us do it again.
1, 2, 3. Okay, there we go. I got 0.8.
Alright, let's keep going. Let's do 50.
Alright, 1, 2, 3. I think I put 1 first.
Yeah, so I was there, right? And that's probably me too.
1, 2, 3. 0.89. Let's just check which was the last one.
Yeah, so this is a little bit bigger. So
Yeah, let's do 0.6 again. Let me try to.
I'll just see how it lines up, right? So that's 0, 40 there.
1, 2, 3.
I think that was it.
Yeah.
I'll go again.
1, 2, 3. Okay, I got 0.93.
That makes more sense. So 0.93. The next one was 0.89, so let's do 0.4 now.
Alright. 1, 2, 3. I got 0.74.
Makes sense.
Next.
30.
1, 2, 3.
Might have been a little late.
Yeah, little. 1, 2, 3. 0.52.
That makes sense.
1, 2, 3. Okay, I got 0.53.
That's a 30, yeah.
1, 2, 3. Alright, 0.5.
That's okay.
Yeah.
And then the last one.
0.1, right?
Okay.
Well, let's wait. Give me a second. Alright. 1, 2, 3. Alright, I got 0.36.
Alright. So that's, along those lines. You're gonna have some outliers. Look, this, what I try to show with the graph is that what you're gonna expect is stuff is not gonna be perfect. Where we're gonna have little errors here and there.
Of course, because there's not a consistent.
Yeah, we're not
And when you
perfect.
multiply it by itself, it's gonna be kind of weird.
Correct. But that's it for just the setup and the first run of our lab. The rest of the kids have done their labs and they're working on the data right now. Thank you very much. Say it again?
So, sir.
It would go from 100 to 10 because you only wanted to measure the 90.
Right, that's what you're trying to do, yeah.
Okay, bad.
So,
So it started at 100 and I'll start it when it gets to 10.
That was body average.
Okay, ready?
So, try out that.
Ah! Okay. Here we go.
One from.
go ahead, guys.
I don't know if I got it exact.
You can try again.
So, do we do that for 0.2?
Do I write it down though?
No, only if you're happy with the measurements. So if you think you might have gone too long or too quick, then you could redo it.
Okay.
You know what I
Let me
mean?
just write it down just in case. Okay.
3, 2, 1.
Ah! Okay, what do I? Should I just put it like that? So that
Yeah, go a little after it. Go a little after it.
Right here.
Go a little after it.
Oh, wait, it's the clock. 1, go.
Okay. I think that was good.
Yeah, looks good. So start making your measurements, okay?
And so.
And then they like.
What? I thought you go from 10 to 1, and that's the 90.
like that because the last one goes to that.
Wait.
We'll put it down to
I'm so
0.1.
confused.
3. Make sure they caught it.
Why do you just have one?
Let me max out
Wait,
radio.
we've only done one so far.
Okay, that's it. From 50, right?
Oh wait, I just realized something. How angles are not gonna be the same.
Yeah, that's what I was saying. But
It doesn't matter, guys. It doesn't matter.
I have a question.
Okay, then yeah.
Am I tripping?
You have this one. Yeah. So you. The second it's done. right,
And that's
zero.
point 1.
And that's that's point 1. You put the time you just got right there. Then you do the same, but for 90, put the time right there. Then you do the same for 80, put the time there. 70, 60, 40.
Yeah,
That's it, that's it.
yeah. So it just goes down to 7.
that's going
up, I mean, but
this is going farther than
Right.
Yeah, that's what I'm saying.
point 1.
It's like how's the furthest distance gonna have the least time?
Maybe it's the other way around, but you're still measuring.
Exactly.
You're still measuring
Exactly.
too much.
Yeah.
No, you put that in time. This is time squared.
Because I was thinking, because if it's like, I
Okay, then we'll just figure
You know what's
out.
quite strange though? How did you go down so much?
That's
You got 150, 145, 130, 118 like 3 times in a row somehow. like for this one, we tested
You're
so
gonna
much.
rub the pencil.
And then we got 1.11. It really doesn't look
You're
good.
gonna 3 plus.
Yeah, you just get the time. Yeah.
Matthew's just
So,
Yeah,
That
on
was
0.1, we got 1.
Yes. Well, no, that was the first time because we went from 10 to 90.
0.3.
Oh, yeah.
To 100, to 100, to 100.
And we got 1.35.
Exactly right.
So, you 8, we got 8.
there. There's one up and down.
Alright.
Like it goes down and then it goes up
And
again.
then that's
Yeah.